Hi, this is a presentation on regularized evolutionary population-based training. This presentation is for the GECCO Conference 2021. Introduction. Deep neural networks, or DNNs, are complicated to train and they're prone to overfitting. The regularization of DNNs is important to their performance. However, there is a problem. There are many possible ways to perform regularization, and thus it's impossible to explore every one manually. The solution is to perform automatic meta-learning for regularization. There are many different approaches, including Bayesian learning, reinforcement learning, and evolutionary optimization. There are many different DNN components that can be optimized, including loss function, weight decay, initialization of weights, and also batch form layers. There are three types of fitting. There's underfitting, overfitting, and good fit. The purpose of regularization is to prevent overfitting and allow us to have good fit on the model and the data. Loss function meta-learning is a promising way to regularize neural networks. They do not add any computational costs and they have very good performance. The drawback is that we must train each network fully during evaluation, and also deep neural network training is an inherently deceptive problem. It's easy to overfit to the validation set, and the validation noise can lead to problems during training. On the right, we can see a cross-entropy loss function, which is used by default. Cross-entropy performs decently, but has issues which loss function meta-learning can overcome. For example, it can lead to overfitting. Here is our main method and proposal to perform automatic meta-learning for loss functions and regularization. It's called evolutionary population-based training. It solves the drawbacks of existing approaches to loss function meta-learning. It contains the following components which synergize well together. First, it contains a evolutionary variant population-based training that interleaves training and loss function parameter tuning together. It's more computationally efficient and does not require retraining of the networks during evaluation. The second component is novelty pulsation, which is used to overcome deception in DNN training. Networks that learn well at first may not converge to the highest performance. The third component is population-based knowledge distillation. This allows us to reduce overfitting to the validation set and reduce evaluation noise. Here's some background. The first one is background of population-based training. Population-based training, we repeat two phases. In the first phase, we exploit and copy weights from good networks to bad ones. In the second phase, in explore, we perturb network hyperparameters. This process repeats until we converge to a final good performance or trained network. This does not work well for a large number of hyperparameters. On the right, you can see a visualization of population-based training. Another background component is loss function optimization. These include GLOW, which involves a symbolic graph of functions using needs, and also Taylor GLOW, which uses a third-order Taylor series approximation with A parameters. It has less parameters than GLOW and can be tuned with state-of-the-art black box optimizers like CMAES, and works better on many architectures. On the right, you can see the equation for Taylor GLOW. Novelty pulsation selection are used to improve the diversity of the population and prevent deceptiveness in the fitness landscape. It computes a novelty score for all the individuals in the population. The most fit individuals are selected, and the most novel in these fit individuals are preserved in the next generation. This novelty-based selection is activated at regular intervals during evolution, hence the name novelty pulsation. Another background component is knowledge distillation. In knowledge distillation, we train a student model to mimic teacher model. The student trains using a target of the linear combination of the teacher's predictions and the data labels themselves. The student model can learn better due to the label smoothing effect, which also is a form of regularization. Here's an overview of how EPBT works. There are three phases. In the first phase, we start off with an individual composed of new hyperparameters, model weights, and fitness value. Hyperparameters that we optimize include learning rate schedule and the Taylor GLOW loss function parameters. In the first and second phases, we select the best individuals from the population, and we generate new hyperparameters using these best individuals through mutation and crossover. And in the last and third stage, we evaluate all the individuals in the population, leading to an updated model and also a new fitness value. So hence, during evaluation, we train the model on some data sets, and the fitness return is the performance of the model on that data set. We use standard genetic operators such as uniform mutation and uniform crossover, tournament selection, and elitism for preserving best individuals into the next generation. Here's the pseudocode of EPBT. In the first step, we perform the selection operation. In the second step, we perform the mutation and crossover operations, and we update the hyperparameters. In the third step, we evaluate the model using the updated hyperparameters, which allows us to define a loss function learning schedule. And after training and evaluating the model, we return the performance of the model as fitness. And the best individuals from the current generation are reserved into the next generation. In EPBT, novelty pulsation is turned on every T generations. The top M individuals of the population are selected using fitness. And then the K most novel elites from the M individuals are preserved into the next generation. The behavior metric that we use for novelty is a binary vector for the DNN predictions from a random subset of data. By using this as a behavior metric, it allows us to discover models which null or fit and improves the population diversity. There's no need for an archive with novelty pulsation because we only use the current individuals. We only use individuals from the current generation to compute novelty and compare it against. By not having an archive, we reduce computational costs and do not require additional bookkeeping. Population-based distillation is an enhanced version of knowledge distillation that is used to help prevent overfitting of the validation set. In PBD, we basically use the best model from the previous generation as a teacher-trained student model. The loss function we use is a linear combination of the teacher's predictions and also the ground truth labels from the data. As you can see, there's a term alpha, which determines the influence of the teacher model predictions over the ground truth labels y. And this alpha value starts off small initially and slowly increases over training. So it becomes larger as the teacher model becomes better and performs better. For our experiments, we evaluate EPBT on two data sets, CIFAR-10 and SVHN. These two data sets are commonly used for many deep learning benchmarks. We also split a small validation set from CIFAR-10 and SVHN to evaluate for the purpose of evaluating models during EPBT evaluations. All of the experiments are performed on the machine with 8300 GPUs. The population size of EPBT is 40, and we take a total of 3 to 4 days of GPU compute for each experiment. On the right, you can see some images of CIFAR-10 and SVHN respectively. Here we first evaluate EPBT on ResNet32 on CIFAR-10. ResNet32 is a medium-sized network with around 400,000 parameters. We compare it against two baselines. The first baseline is not using EPBT, thus single model training with a fixed hour schedule. The second baseline is the original PBT, our implementation of it, and it optimizes the learning rate of the model. As you can see from results, EPBT outperforms both. It learns faster and reaches a higher fitness value. As you can see from the plot, the red lines, EPBT, and the blue and green lines are baseline 1 and baseline 2, respectively. We also try EPBT on wide ResNet architecture. So we try it in order of increasing network depth from wide ResNet 10-12, 15-8, 22-6, and 28-5, as you can see in the plots below from left to right. The performance is larger for shallower networks than the deeper ones. Blue line shows the performance of the baseline, and the green line shows the performance of EPBT. We will see that EPBT outperforms the baseline on SVHN for ResNet32. We learn faster, and there's also lack of overfitting when compared to the baseline. In the baseline, we can see that the performance starts to drop after 20 and 30 epochs respectively, but that does not happen with EPBT. Here's a performance summary showing the number of training epochs required for EPBT to exceed the final test accuracy of the baselines. As we can see, it takes around 80% of the training for EPBT to exceed all of the baselines for all the data sets and all of the different architectures. In the second table, we see the mean standard deviation over 5 runs of the final test accuracies on CIFAR-10 and SVHN. As you can see, EPBT is able to outperform all the baselines in all the architectures. Here we analyze loss functions that are discovered using EPBT. As you can see, the loss functions change over the generations. We start off with relatively convex and parabolic loss functions early on training, as you can see from the darker lines. This shows that the loss functions that discovered resemble the bicol shape function from below. And this kind of shape, this kind of function shape allows us to incur a higher loss when y is close to 1. And this in turn, this allows us to regularize against overfitting. These shapes discovered are consistent with what was discovered glow and teraglow without EPBT, and it happens early where it matters, where regularization is very important to train. Later on, the loss functions become more concave and start facing downwards and emphasizes better accuracy by having lower loss values at y equals 1. This can be seen as the lighter lines in the plot. We also have a visualization of the cross-entropy loss in the lower right corner as well for comparison. Here we analyze the learning rate schedules discovered. As we can see, the learning rate starts high and decays with cycles and bumps. It resembles the cyclical learning rate schedules that are discovered by hand. There's no pattern for momentum, but there's a clear cyclical decaying pattern for learning rate. The top plot shows a linear scale, while the bottom plot shows a log scale. For future work, we plan on creating more dynamic loss functions, which can adapt to the current state of training as input. This allows us to basically create functions which can adapt to idiosyncrasies in the training and also the data set itself. In addition, we plan to combine neural architecture search with loss function optimization. So we will optimize both loss functions and the architecture of the network at the same time. We plan to use algorithms like CIFAR-10 for performing architecture search. We also plan to perform ablation studies to determine the effects of each component of EPBT. Here below, you can see an overview of how CIFAR-10 works and how it can be used to discover new network architectures. In conclusion, EPBT discovers loss functions that outperform hand design ones on CIFAR-10 and SVHN. The loss functions discover change shape and adapt over the course of training. Also, it's an effective way to perform automatic meta-learning for regularizing and training of deep networks. EPBT is scalable to a large number of hyperparameters and sufficient due to the interweaving of training and hyperparameter tuning, thus allowing us to save computational costs and not fully train a network during each evaluation. That's all for the presentation.